The purpose of Chapter 5 is to address functions that we have yet to look at in this course. In Chapter 5, there will be no new concepts, so everything we learned back in Chapter 2 concerning derivatives and tangent lines and slope, and everything we learned in Chapter 3 with relative extrema, concavity, everything we learned in Chapter 4 regarding integrals, area, the fundamental theorem of calculus, average value, everything we've studied since Chapter 2 still holds true. In Chapter 5, though, we're going to look at functions that we haven't addressed so far in this class. So in section 5.1, we're going to look at derivatives. So all those concepts we know about derivatives are still true, except we're going to look at derivatives from the point of view of a natural log. So this first slide will serve as a little review of natural log properties and even what a natural log function is. So the first thing we need to keep in mind is that in general, not a natural log, but a log is an exponent. So you might recall this back from your Algebra 2 and Pre-Cal days, but if you want to take log base a of x, and if that's equal to y, and you want to convert that to its exponential form, we would write x equals a to the y. This little saying up here at the top kind of tells you how to do that. It's telling us that a log is an exponent. So we know that the exponent is what the log is equal to. The base of this log is the base for that exponent. So just a little way to maybe remember how to change logs to their exponential form. What we're going to really focus on this chapter is not just logs, but natural logs. And if you need the little reminder, a natural log is just a regular old log, but it has a very special base of e. So if we want to change a natural log to its exponential form, if we have ln x equals y, we would know that x is equal to e to the y. And that may or may not become a handy little thing to know throughout this chapter. So the main thing you have to kind of realize about this is that an inverse of a logarithmic function is an exponential function. Logs and exponential functions are inverses of each other. And we're going to use that little property throughout this entire chapter. So a lot of little ideas that you need to kind of remember about natural logs. Again, we're going to be using these all throughout this chapter, so please kind of commit these to memory as quick as you can, and maybe some of these you even remember from prior classes. ln1, you might be tempted to want to use a calculator to figure that out, but a lot of the times you're not going to have a calculator, so you're going to need to know that the natural log of 1 is 0. In part B, the natural log of e is 1. If you ever have an ln where two things are being multiplied on the inside, we can split that into two separate natural logs, and then a plus will be in between those. If you ever have a natural log of something to a power, we can bring the power down to the front of that natural log. And if we have a natural log of a quotient, we can write that as two separate natural logs, but with a minus in between. And one thing you might want to jot down on this side, it's not here in this PowerPoint, but don't make this mistake. If you ever see a natural log of something plus something else, that is not equal to ln A plus ln B. So be careful with that little mistake, a very common mistake that usually can happen if you're not totally aware of these properties that we're using. Okay, so let's practice using a few of these properties real quick. We're going to need to use these throughout this course, so we might as well practice using these. Here we have an x times an x plus 1 squared. We're multiplying two different things, so we can separate this into two separate natural logs with a plus in between them. On this second natural log, it has a power. ln of x plus 1 squared, that power of 2, is being applied to the x plus 1. So we can move that power of 2 to the front of the natural log, and it's just that simple. If you wanted to expand it, that would be the expansion, and maybe that's going to serve a purpose once we start trying to take derivatives of natural logs. What if you have a bunch of natural logs that you want to condense down to one natural log? Well, in this case, any positive natural logs would be in the top of a fraction, any negative natural logs would be in the bottom of a fraction. So you'll notice, since the ln, well, the first ln is a positive ln, that x squared plus 1 could be in the top of a fraction inside a natural log. Since the second two natural logs are negative, the inside part of the natural log would go to the bottom of a fraction. So the x plus 1 and x minus 1 would go to the bottom of a fraction. We can do one more thing. This 3 over 2 in the front is in front of an ln. So if we wanted to, we could move that back to the inside of the natural log as a power. And just as a little side note, these two right here are a difference of squares, or can become a difference of squares, so we can just rewrite that as x squared minus 1, just to make it look a little more simplified. Okay, so like I was mentioning in the very opening slide, this chapter, nothing has changed concerning derivatives. We still know how to find derivatives so that we can find tangent line equations or slope. We can still find extrema, concavity. We can still do all those things. It's just now we're addressing a function we've never seen before in this class. And it turns out that the derivative of the natural log of x is equal to 1 over x, assuming x is greater than 0. And you have to keep that in mind about natural logs. Natural logs are always positive, so that value of x can never be negative. Okay, unfortunately, a lot of the times you probably won't just see ln x as the thing you're trying to take the derivative of. So when you don't see a plane x, we have to think about using the chain rule. So really the version of this derivative that I hope we all commit to memory is, what if we have stuff on the inside of a natural log? Well, the good news is, if the derivative of ln x is 1 over x, then the derivative of ln u is 1 over u. But we have to multiply by the derivative of u because we're using the chain rule. That u prime is because we're using the chain rule. Just as a little side note to make, every once in a while, and it's super rare, you might run into a natural log with an absolute value on the inside. Luckily, as you can tell from this formula below, it changes nothing concerning the derivative. Okay, so let's try to practice using this new little formula for taking a derivative concerning a natural log. Here we're trying to take the derivative of the natural log of x squared plus 3. So the derivative of a natural log you can almost just view as this formula and don't overcomplicate it. We know it's equal to 1 over u. In this case, our u is equal to x squared. This is our u is equal to x squared plus 3. So the derivative would be equal to 1 over x squared plus 3. But just don't make the little mistake of forgetting to multiply by u prime. The derivative of u, the derivative of x squared plus 3, is just 2x. And just to simplify this a little more, we can multiply the 2x just to the 1. 2x is really over 1. So we can multiply the 2x to the top, and it'll just be 2x over x squared plus 3. So very simple and straightforward, but don't forget what this represents. This is our derivative, which means it's our slope machine. If we wanted to find slope, we could plug in our x value here and get that value. But for now, we're just practicing using this new derivative rule. What about the derivative of ln x cubed? Well, one big note to make before we even attempt this problem. Ln of x cubed does not mean ln x all cubed. In this problem, x is being cubed. In this other version that I wrote, ln x as an entire thing is being cubed. So be very careful with the way a power is written in terms of what it means. Okay, so we know the derivative of ln u, which is x cubed in this case. Our x cubed is our u here. So the derivative of ln x cubed is just 1 over x cubed. We're just using this formula. But because it's not a plane x, we need to multiply by the derivative of u, and in this case the derivative of x cubed is 3x squared. If we multiply and simplify here, the 3 will stay in the top. Since we have an x squared over 1, The x squared in the top cancels with 2 of the x's in the bottom, and we're just left with 3 over x. A perfectly acceptable way to do this problem. But I'm going to point something out in the next slide, but I'm going to kind of get to it a little bit ahead of schedule here with this one example. And I'm going to call this maybe the sneaky way of doing this problem. We really didn't have to do this problem the way I did it to begin with. We might have realized that we could have used one of those properties from that first slide. Since this power of 3 is on the inside of our natural log, and I guess I can put a little parentheses around this just to emphasize that. Since that power is on the inside of our natural log, we can pull that power out to the front. And then you might even see this could be an even easier derivative if you look at it from this point of view. The 3 just stays in the front, and we know the derivative of ln x is 1 over x. Or to simplify that, it just becomes 3 over x. So maybe a little lesson to learn from this, what I'm calling the sneaky way, is that maybe if you can use properties of natural logs, you should probably approach a problem first by doing that instead of just going to the derivative. Okay, one more problem here, and you might be looking at this and going, we haven't seen limits in a while. But if you're looking at this problem as something you need to be taking the limit of, you might have forgotten something back from 2.1. It's been a while since we've seen this, but I hope you're recognizing this as a problem that's not asking you to actually find the limit. If you recall from our definition of the derivative, the definition of a derivative had the form of a limit as h approaching 0 of f of x plus h minus f of x, all divided by h. And if you look at our problem, it looks a lot like that form. As a matter of fact, it's identical to that form. And you'll notice that piece at the end on the numerator of the fraction is indicating to us what the function was that we're trying to take the derivative of. So bottom line with this problem is this. We just really need to translate this into a little more simplified version of what it's really asking for. So to translate this into something that's a little more straightforward, what we're trying to do is we're trying to find the derivative of the function ln x. And I know it's ln x because that's what I have circled in green. Our function is ln, and I know there's a 4 there, but it's ln of some value x. The reason that 4 is there is after we take that derivative, we want to evaluate it at x equals 4. You'll notice that this 4 is in the place of x in both of these spots. So it's not telling you to take the derivative of ln 4, it's telling us to take the derivative of the function ln x, and then we can plug in 4. So that was really just a long way of explaining a very straightforward problem. If you could kind of get through all the math notation to just see it was actually asking a very simple question. And now since we've learned this new little derivative rule, the derivative of ln x is just simply 1 over x. And if we want to evaluate that derivative at 4, we're just going to plug in 4, which gives us 1 over 4, or answer choice B. Okay, something I kind of hinted at in the last slide, but definitely want to make it clear with these examples. We need to always apply properties of logarithms to simplify prior to taking a derivative. In that last slide, you saw me call it the sneaky way, so to speak, but really that's the way we want to do it all the time. It'll make your problems, if not entirely easy, it'll make them possible to do, because sometimes if you don't use properties of natural logs, that would just leave your problem in a very difficult form. So let's take a look at a few examples. Here we're trying to take the derivative, that's what this notation means, take the derivative of ln 1 minus x to the 3/2 power. You'll notice we have a power inside a natural log. So we can take that power and move it to the front. But be very careful. I've seen this a lot. When you move that power to the front, because that almost feels like you're taking a derivative by pulling the power down, you might feel like you've already taken a derivative, but we haven't taken a derivative yet. We're still going to need to write d dx to show that we still are going to take the derivative. Since we can't use any more properties of natural logs here, we're ready to take the derivative. That 3 over 2 is just going to stay in the front since it's a constant. And from the last slide, we saw that the derivative of ln u, this is going to be our u here. The derivative of ln u is 1 over u. So we don't even have to really think about that. Just write that down. Now the part we have to think about is we need to be multiplying by u prime. The derivative of 1 minus x is negative 1. And other than simplifying it, that's our answer. I'm going to move the 3 to the top here by multiplying. I'm going to move that negative to the front, and then I'm going to distribute the 2 in the bottom. We don't really have to distribute the 2 in the bottom, but I'm going to go ahead and distribute it. And we're going to end up with a final answer of 3 over 2 minus 2x, and then just don't forget that negative in the front. Okay, here we have a function, ln square root x squared plus 1. We're trying to find the derivative. So we need to write this in a manner that will let us take a derivative. The first thing I hope we'd all do, because we've been doing this essentially every problem that has square roots or cubic roots or what have you, is to change that root to a power. Once we change that root to a power, just like the first example I did on this slide, we can take that power, since it's on the inside of a natural log, and move it to the front of the natural log. Once we do that, we've used all the properties that we can apply, and now we can take the derivative. That 1/2, that constant of 1/2, will stay in the front, so we'll have that 1/2. And then here, it's the derivative of stuff. It's not a plain x, so this x squared plus 1 is our u. So the derivative of ln u is 1 over u, so 1 over x squared plus 1. Can't forget to multiply by u prime, the derivative of that stuff, and of course that's just 2x. If we move the 2 to the front with the half, that'll just disappear and become a 1, and of course that x we can multiply to the top with the 1. So our final answer just becomes x over x squared plus 1, and that is our derivative. That's our slope machine. One more problem, and it's something I talked about in the in the last slide, and that is, how do we take the derivative here of ln x all to the third power? Well, don't make the mistake I was kind of referring to back in that last slide. Ln x all to the third power does not simplify to be 3 ln x. We can only move the power to the front of the ln if the power is on the inside of the natural log. So we can't do the problem this way. But maybe it's not that difficult anyway, even though we can't use this little property here to make it easy. Maybe it's not that difficult of a problem in the first place. And the reason I say that is because we need to realize we don't have a plain x to a power. We have ln x to a power. And that's okay. We just need to realize when we don't have a plain x to a power, we're trying to use the chain rule. So I'm going to call u ln x. If we call u ln x, then we're just left with the derivative of u cubed, which is very, very easy. So to take the derivative of u cubed, we'll bring the power down, we'll leave the u alone, and we'll reduce the power by 1. By the chain rule, we also need to multiply by u prime, so don't forget about that little step. So what is u prime? Well, u prime, like we've learned new in this lesson, u is ln x, so u prime would be 1 over x. And once we take everything and plug it back in, we'll be left with that derivative. Technically, we could circle that as the answer and kind of move on, but I'm going to kind of just clean it up just a little. In a lot of problems, I hope you got used to moving that u prime to the front just to kind of clean things up a little bit. And when we move that 1 over x to the front with the 3 and multiply them, we'll end up with 3 over x, and then ln x all to the power of 2. Okay, a few more problems to hopefully review some of the derivative skills and concepts we've had from the past, and also applying this new derivative of a natural log. So here we have the function x times ln x. And if you're quick to realize this, which I hope you are, you'll see that this is a product rule because we're taking one function and multiplying it by another function. Since we're doing that, I like to rewrite it with parentheses around each of those functions, just to emphasize that idea. The product rule says that we need to take the derivative of the first function, which is x, so that's going to be 1, and then we leave that second function alone, so ln x stays ln x. We put a plus sign, and then we switch those roles, so to speak. We leave the first function alone, so we're going to leave that x alone, so the x stays there. And then we take the derivative of ln x. The derivative of ln x, as we learned in this lesson, is 1 over x. So very straightforward here, and we can of course simplify this by just saying 1 times ln x is just ln x, and then x times 1 over x is just 1. So we'll have ln x plus 1, and that's our derivative, y prime. In the second example, a very important skill, hopefully just needs a little reviewing because you mastered it. We want to find the equation of a tangent line, and as soon as you see that, I hope you're thinking of the point-slope formula. So we need a point and we need a slope. Luckily, we have the point out of the way right now. We have our x and we have our y. So we need a slope, which means we need to take the derivative of our function. Luckily, this can't be any more straightforward. The derivative of x is 1, and again, we just learned in this lesson, ln x becomes 1 over x. We want to find what the slope is at 1, 1, so we need to plug 1 in for x. When we plug in 1 in for x, we get a slope of 2. So I'm going to go ahead and write that little fact out in words, just because we haven't really practiced this in a while, and just to make sure we're all on the same page. What that means, y prime equals 2, is that at 1, 1, the slope of our tangent line is 2, and once we realize that, we can plug all our values in. X is 1, y is 1, and our slope is 2. And just as a reminder, you are more than welcome, if there is no need to simplify your equation, just to stop right there and circle that as your answer. I'm going to just simplify the answer so you can see what it looks like simplified, but either of those answers would be acceptable. In the last example, we're going to be doing quite a few things here, but the bottom line is we're trying to find any relative extrema. And as a review from chapter 3, that's another way of asking for maximums and minimums. So as a reminder, we have to first find critical points. So to find those critical points, we need to take a derivative. And in this case, we have a function over a function, so that's going to be a quotient rule application. So let's go through the quotient rule. The quotient rule, if you memorized it using my little memory technique, said low d high. So we're going to take 2x and write it, and then d high, the derivative of the top, the derivative of ln x is 1 over x. So it's low d high minus high, which is ln x, times d low. The derivative of the bottom is just 2, and then we divide by low, or 2x squared. To simplify this, it simplifies kind of nicely. The x's in the first term cancel, so we're just left with a 2, and then I'm going to take the 2 at the end of ln x and move it to the front to kind of clean it up, and then 2x quantity squared becomes 4x squared. Okay, so to find critical points, as a quick review, we need to set our derivative equal to 0, and don't forget this, we also have to check if it's ever undefined. So let's do the first part of setting it equal to 0 first. When we set a fraction equal to 0, that bottom part, when you multiply it to the other side, essentially just goes away. So we're really just setting the top equal to 0. When you subtract 2 and divide by -2, we'll end up with 1. And if you want to refer back to the very first slide for this, the value of x, so that when you take the ln of it, gives you 1, is equal to e. And in case you're not up to speed with e, just keep in mind e is just a number. It's kind of like pi. It's a letter that's standing in place of a number. And if you have forgotten this, something you're going to want to commit to memory so you know roughly what e is. E is about 2.718. Okay, so we at least have one critical point. We got one critical point when we set our derivative equal to 0. But since our derivative was a fraction, we also need to figure out where is y prime undefined? And that of course happens when the bottom is equal to 0. Luckily, this is nice and simple to solve. The value of x that gives you 0 is 0. But we need to think about this value that we're getting, because maybe it really isn't a critical point. If you think hard about this, and if you know what you need to know about natural log functions, you'll realize that we can't consider that as a critical point. It is a value we got, but we can't consider it as a critical point. That can never be a max or a min, because ln x is never 0 or negative. So it's just not something we can consider. On top of that, maybe you've noticed also the function ln x over 2x is undefined at 0. So that would be another reason that couldn't be considered a critical point as well. Okay, now that we've gotten all the math and calculus out of the way, or the algebra and calculus out of the way, now we can go straight to our little sign chart and figure out, is the point E a max or a min? So we're going to set up our sign chart, pick a number to the left of E, pick a number to the right of E, and plug it into our derivative. Here I'm going to pick, or to the left of E, I'm going to pick 1. Seems like a logical number. We could have picked 2, but 1's easier to maybe plug into your derivative without a calculator. If you plug 1 into your derivative, you'll get a y prime value of 0.5. We don't really care so much that it's the number 0.5. We care that it's a positive value. To the right of to the right of 2.718, to the right of E, I'm going to choose the value of 3. And if we plug that into the derivative, we'll get a negative value. If a derivative changes from positive values to negative values, we know that that is a relative max. And that's how we can finalize this answer. We know there's a relative max at x equals E. And if you had to write a justification of that, you would put because the derivative changes from positives to negatives.